Okay, so it's time now to start our second session, which begins from 15:31 p.m. the UK time. So we now move on to the directions of net zero manufacturing and waste recycling. And in that space, we have six speakers next coming, starting from Mr. Dominic from University of Manchester. So Dominic, you are welcome to share your thoughts with us.
Thanks. Hi, everyone. My name is Dominic. I'm from the University of Manchester, and today I'm going to be talking about plasma electrolytic processes for coating light alloys in automotive applications and how this relates to COP26 issues. So what's the problem? Well, transportation is responsible for about 24% of total global CO2 emissions from fuel combustion, and 75% of these can be attributed directly to road vehicle emissions. So how do we reduce CO2 from road vehicles? Well, to put it very simply, weight is imperative to vehicle efficiency. So what we're looking to do is reduce the weight so we can burn less fossil fuels. And this weight reduction is also important for enabling alternative power systems such as electrification. So where we've got lightweight designs, what we require is lightweight materials. So today I'm going to be talking about light alloys, namely those of aluminium and magnesium. So these aluminium and magnesium alloys have low density, and they also have what's called a high specific strength. So they've got a high strength proportional to their density. And this is very important for weight saving applications. But whilst these materials have a lot of benefits, they also have their limitations, and these can include things like corrosion and wear resistance, hindering them from certain applications. So a solution to this is to implement a coating. So my research is focused on a technique called plasma electrolytic oxidation. And in this technique, we're taking a component and submerging it in an aqueous weak alkaline electrolyte and applying an electrical potential. This promotes the formation of an oxide coating, and where we're applying quite high voltages, this results in a sparking process, which assists the formation of the coating, and we end up with quite well adhered and protective ceramic oxide coatings, and we can do this on metals, including those of aluminium, magnesium, and titanium. So these coatings have excellent corrosion and wear properties. So how can we use this in automotive design? Well, I'm going to go over a few quick examples. So one is the implementation of magnesium as a material for making engine blocks. So engine blocks are traditionally made out of cast iron or cast aluminium, and these are quite heavy. But there's a lot of interest in using magnesium for these applications. However, there's two main drawbacks. The cylinders require quite high wear resistance, and the engine's a very corrosive environment. So magnesium alloys often can't stand up to this test. However, a potential solution is the application of PEO to this component, so we can produce a magnesium oxide protective coating on it, which will improve its wear and corrosion resistance while maintaining the low weight of the magnesium material. Another application of PEO for lightweighting in automotive design is brake discs. So traditionally, these are made out of cast iron, and they perform very well and last quite a long time. However, they're extremely heavy. So in top-end sports cars, they develop ceramic composites, and these perform very well. However, they're too hard to produce, and the cost is extortionate, so it's not feasible to spread out to all cars. However, a potential further solution is PEO-coated aluminium alloys for brake discs. So aluminium, you're saving a lot of weight. However, the aluminium alloys are typically quite soft and have low wear resistance. However, researchers have been working on PEO-coated aluminium alloy brake discs, and they've produced these light brake discs that actually have superior wear resistance to the traditional cast iron components used for this. And then lastly, I'm going to touch on thin PEO coatings for durable bonded structures. So where we have aluminium structures in place of steel structures, typically they're joined via adhesive bonding. And where we're doing adhesive bonding, we're always concerned with the bond durability. So to improve the bond durability, aluminium components undergo surface treatments, conventionally anodizing for this process. However, I'm personally looking at PEO as an alternative to anodizing for the preparation of adhesively adhered components. So this could have a number of components because a number of advantages because the PEO process is very robust due to the sparking nature, so it would allow the streamlining of the manufacturing process. And that's my talk. Thanks for listening.
Thank you very much. Thank you very much, Dominic. This was fascinating to learn this new alloy type. We'll catch up in the Q&A more on it. So next I'll invite Jonathan from University of Cambridge to tell us about biofouling.
Hello. So my name is Dr. Jonathan Bean. My research is sort of focused on increasing the amount of time or decreasing the amount of time it takes to find new materials. And so we're using a lot of computational methods and artificial intelligence and that kind of thing. And so this work was done in conjunction with the University of Cambridge, Materials Nexus, which is a new spin-out company, and LSBU. And so what we're trying to do is to essentially automate the development of new coatings. And so to give you an idea, one of the biggest problems associated with new materials and products is that they are, in most cases, for example, the laptop that you're watching me give this presentation on, put on a ship and transported 10,000, 20,000 miles, sometimes even further when you have a very complex supply chain. And so what I'm showing you here is what's called fouling, which builds up on the bottom of ships. And it's a really big problem because it slows down the ship as it progresses through the ocean, and so therefore increases the fuel usage of that particular ship. And so shipping actually contributes, because largely of this effect, to 2% of all worldwide emissions. And so if we can reduce this fouling effect, we should have a significant effect on the carbon which is emitted into the atmosphere. And so I've already mentioned that the drag increases, and so it gives approximately a 40% increase due to this fouling. And in fact, one of the major issues associated with fouling is that many of the current paints which are existing on the market are formed from a copper oxide derivative material, which can leach into the ocean and give very, very bad sort of effects into wildlife and get into the food chain. It's very, very likely that in future years, this material is going to be banned, and it's a case of when it's going to happen, not if. And so we need to find new alternatives to these materials, which are what's called non-biocidal, so they don't have nasty chemicals in them which go into the ocean, but also stop this fouling effect. And so the way we're doing this is using this artificial intelligence engine which we developed. Broadly, the way it works is that we predict a range of different properties based on simulation and some experiments, and then we use the AI in order to optimize where particular choices of materials in terms of elemental composition and different processes in terms of manufacturing in order to come up with these predictions. And so to give you an example, what we can do is make certain estimations in terms of, say, how much CO2 footprint a material is going to be because of, say, the temperature required to put it into an arc furnace to melt it, or the particular processes in terms of rolling. And so once we've optimized this, we can come up with a series of proposals. And then one of the nice things that we have with this collaboration is that we can then actually go in the lab and test these different proposals. And so using this sort of de novo materials design, using some techniques at LSBU, we can actually find coatings which can be longer lasting, and so therefore need to be reapplied less time, and so therefore there's a saving there, but also means that the fuel economy is going to be increased. And then of course we're looking for things which are non-toxic, so generally doesn't contain heavy metals and will have low VOCs and this kind of thing. Thank you very much for listening, and happy to take questions at the end.
Thank you very much, Jonathan. It's good to see some accelerated research on de novo material design with the use of AI and quantum computing. Hopefully we'll propel that area more. but it's apparent that waste is increasing day by day, more and more, and we are more than ever concerned about waste recycling now. And so we have now 4 accident talks coming ahead of us about the issue of waste recycling, starting from Tasnuva from LSBU.
Can you hear me?
Yeah, Tasnuva, can you do full screen? Press F5 maybe?
Yes.
Good to
Is
go.
it full screen now?
Yeah.
Thank you very much. Good afternoon, everyone. I'm Dasnuva Khalik. I'm a postdoctoral research associate at London South Bank University. Currently, I'm working with Dr. Saurav Goel on ice-phobic and durable coatings for the aerospace and energy sectors. Today, I'm going to talk on plastic recycling and sustainability, a roadmap to combat climate change. Plastic is one of the most greenhouse gas intensive industries in the manufacturing sector and the fastest growing. Greenhouse gas emissions from plastics are accelerating climate breakdown and threatening our ability to maintain a survivable climate. Nearly every piece of plastic that exists in the world originated as a fossil fuel, and greenhouse gases are emitted at every stage of the plastic's life cycle, from its extraction and transport, refining and manufacture, through to waste management. In 2019, only production of plastics added more than 850 million tons of greenhouse gases to the atmosphere, the equivalent of 189 coal-fired power plants. By 2050, the accumulation of these gases will account for up to 30% of total remaining carbon budget. That's the amount of extra carbon the planet can tolerate before tipping global warming over 1.5 degrees. The increase of plastic products in the last several decades has been extraordinary. Over 380 million tons of plastics are produced globally every year. 50% of all plastic produced is for single-use purposes, used for just few minutes and then thrown away. Plastic waste that isn't recycled ends up entering our environment, polluting our oceans and causing damage to our ecosystem. Approximately 10 million tons of plastics are dumped in our oceans annually, and approximately 1 million marine lives are killed by plastic pollution every year. It is estimated that there will be more plastic in our oceans than fish by 2050. However, only about 9% of the 8.3 billion tons of plastic produced since 1950 has ever been recycled and produced in useful products. There are several economical and technical reasons that not all common types of plastics can be recycled. For example, polystyrene often is not recycled because it is difficult to sort from other types of plastic waste and easily breaks into small bits, which can clog up sorting machines and cause them to break down. Recycling plastics reduces the amount of non-renewable energy used in the plastic making process, as creating new items from existing plastic uses significantly less energy than creating plastic raw materials. And this also, of course, reduces strain on the power grid, meaning that oil and coal is saved and carbon emissions are reduced. Except ABS plastic, the other commonly used plastics are more or less toxic and have adverse effects on human health. Some of them are carcinogenic as well. ABS plastics are one of the non-toxic and non-carcinogenic plastics among the commonly used plastics. ABS plastics can undergo recycling and reforming into consistent 3D printer filaments without the addition of virgin material. Axion Polymer UK's carbon footprint analysis showed that recycled ABS plastics reduce carbon footprints by approximately 89% than their virgin alternatives in the UK. As ABS plastics are non-carcinogenic, inexpensive, and 100% recyclable into 3D printer filaments, emphasis should be given on recycling ABS plastics, thereby reducing the amount of plastic being manufactured and help the climate change. Thank you very much, all.
Thank you, Tasnuva. That seems like a nice prospect of ABS. Let's move on to a new direction in this same space, which is going to be stemming from nature. So we can learn a lot from nature, which is what Nirmal's talk is going to be focused on. So Nirmal, please feel free to share your slide.
Hello everyone. Myself Nirmal Kumar. I am working as a Newton postdoc fellow with Dr. Saurabh Goyal at London South Bank University. So today I am going to present mitigating climate change by nature inspiration. So basically is how nature inspiration can help us to prolong the planet life and suitable for life. As we know, climate change has become the potential threat to life on Earth, basically due to the industrialization and our huge energy requirements. As our green Earth slowly becoming dangerous for the living species, basically due to the our industrialization. Day by day, increasing industrialization, increasing the carbon dioxide gas in the environment, as well as we also cutting the trees. So deforestation, also basically the industrialization continuously producing the carbon dioxide gas, but carbon dioxide gas consumer is the forest, but we are destroying the forest also. So this is increasing in a most massive way carbon dioxide gas. As we know, carbon dioxide gas is part of the greenhouse gases. So CO2 major amount of CO2 is consumed by the ocean. So ocean water is getting acidified and affecting the aquatic life, and CO2 also increasing the planet temperature, which directly affecting our glacier. It is estimated that in 250 the many glacier will melt, and in many city may get submerged into the water, and this also life disease for humans producing by the carbon dioxide gas. So main climate problem solution, how we can tackle this problem, like carbon dioxide continuously getting increased. So as we know, like we are burning coal, petroleums, and many other industrial process. Everything is producing carbon dioxide gas and freely released in the environment. So basic things is like this is a one-way process, continuously increasing carbon dioxide gas in the environment. So how we can combat with this process? So we must learn from the nature, because nature already have some solution for every problem. So this nowadays called nature inspired technologies. Suppose, as we can see this image, in human in their respiration system taking oxygen and releasing carbon dioxide gas. But on the other hand, tree, their photosynthesis process taking carbon dioxide gas and releasing CO2. So they are two biological machines complementary each other. One is a consumer, another one is a producer. So by this way, they are not destroying the climate of the planet. But in our case, by industrialization and deforestation, we just continuously increasing carbon dioxide gas, which destroying our climate. Therefore, there is some research is going on. As we can see, electro-oxidation of the carbon dioxide gas. So by developing some catalyst, carbon dioxide gas can be converted into the fuels, but this process is triggered by the electricity. So electricity also must be produced from the green sources. But another research also huge requirement like artificial photosynthesis, just the counterpart of the natural photosynthesis, like develop such a material that can arrest carbon dioxide molecule from the environment and convert them into biomass or fuels. So by this, we can reduce the burning of fossil fuels and also arrest carbon dioxide from the environment. But this process must be triggered by sunlight. So this energy can be green go. We can say green go. Suppose like industry, some industry producing carbon dioxide, massively carbon dioxide, then we must put another plant adjacent to that company, which can arrest the carbon dioxide gas. So there will be both, like one will be the producer, another will be the consumers. So this research is going on and some research already done, but there is many problems like carbon dioxide cannot be arrested at atmospheric. It can be only in laboratory scale or a high concentration of carbon dioxide can be arrested. Thank you.
Thanks a lot, Nirmal. That was really wonderful to see how nature balances everything so nicely without having anything as a requirement that what we are struggling with. So let's move on to the new topic now with Charlie from Queen's Belfast.
Hi, everyone. Is that full screen for you?
Yeah, you can see Charlie. Go ahead.
Okay, perfect. Okay, my name's Charlie Farrell, and I am a final year PhD student at Queen's University Belfast, supervised by Professor Adrian Murphy, Dr. Zhao Zhang, and Dr. Rory Dockerty. So essentially, my work is looking at the recycling methodologies of first generation solar panels, more commonly known as photovoltaic modules. So looking at solar panels in an expanded view, there is numerous material types that make up a solar panel, such as the external aluminium frame, the front glass layer, polymer materials, which is the EVA encapsulant, top and bottom side of the silicon solar cells, the Tedlar backsheet to protect the module from weathering, and the junction box for electrical conductivity. So my work is essentially looking at the EVA encapsulant, looking at delaminating PV modules using a technology known as pyrolysis. So heating the module in an inert environment in order to break down the encapsulant in order to recycle the other constituent materials of the panel. So currently PV modules, there's only one sort of main recycling infrastructure, which is based in Europe, which is undergone by a outfit called PV Cycle. And how they recycle these modules now involves mechanical based recycling, which involves the cutting and milling of PV modules, which crushes down the other layers and disregards some of the emissions and the energy requirements in order to manufacture the silicon solar cells. So looking at the waste management hierarchy, ideally the most preferred option is the prevention of this waste. At the moment, the PV module or PV recycling industry, is in and around the area of recycling and energy recovery. So some of the main drivers looking at PV recycling, PV modules were included to the Waste of Electrical and Electronic Equipment Directive in 2012 in Europe, making it law as of 2014 that any supplier or manufacturer of PV modules is responsible for their end-of-life management. So PV modules can be considered as end-of-life once their wattage drops below 80% of the initial quoted wattage at manufacture. So for example, if you have a 250 watt PV module, once it goes below 200 watts with the wattage output, it can be considered end of life. It has a limited lifespan of 20 to 25 years, which is indicated by the manufacturer's guarantee. And as I mentioned previously, the ideal scenario is the prevention of this waste. So the WEEE logo is this black crossed out wheelie bin here in the bottom left, if you can see my mouse cursor. So we're looking at the scale of the problem. The PV module industry has been dominated by first generation technology from about 1980. So the bottom graph in this slide shows a market share of first and second generation PV modules from the years 1980 to 2016. And the first generation technology is shown in the light and dark blue colors, which has dominated the market between 80 to 90%. And there was a report published by the International Renewable Energy Association in 2016, which indicated that there will be approximately 60 to 78 million tons of PV waste by the year 2050. So looking more at some of the constituents in the PV module, the encapsulant EVA, which is used top and bottom side to encapsulate solar cells, it has been used in the industry since the early 80s and is the industry standard encapsulant, mainly due to its excellent transparency and adhesive properties to the other layers, such as the front glass layer and the back sheets. It usually contains 33% vinyl acetate content, which is the monomer shown on the right-hand side, highlighted in red. And it's been proven that the recycling of EVA is the first and the most difficult step in actually recycling first-generation PV technology. So some of the work that we've done with the pyrolysis of PV modules at Queen's University Belfast, we've looked at extensive thermal analysis, looking at used encapsulants in PV modules and virgin grade encapsulants in a nitrogen environment, and looking at how much essential residual mass is left over post pyrolysis. So looking at the used and virgin grade encapsulants, the A and B scenario there in the figure on the slide, the residual mass is approximately 1% of the initial mass going in. This targets the energy recovery area in the waste management hierarchy. It also considers the emissions relating to silicon production and the use of hazardous chemicals. So when panels are effectively recycled using a mechanical method of recycling, when they're cut down and milled, the PV cell has to, you have to employ hazardous chemicals such as an aqua regia treatment or hydrogen fluoride to be able to remove some of the materials on the silicon cell. Then it requires a lot of energy to melt that silicon in order to go back to a melt to create an ingot, and then more energy to saw the ingot to be able to slice the individual wafers. Also, we've looked at some energy values using calorimetry studies. So again, looking at the difference in used encapsulants and virgin grade encapsulants, the calorific value or the gross calorific value, the difference is negligible between the used and the virgin grade encapsulant, and is high and comparable to that of biodiesel and home heating oil. If we're able to look at, harnessing the energy inherent in the PV module, whilst also allowing clean delamination of the panel to recycle the other constituents that could go into, for example, a brand new PV module. So here, just this diagram that I've included is very similar to the butterfly diagram that was made famous in circular economy concepts from the Ellen MacArthur Foundation. What we've done is we've taken the individual life cycle of a PV module and separated into 4 separate steps. So the mining and extraction of raw materials, the manufacturing of the wafers and the module's lifespan and use, and then the end of life treatment. So currently at the moment, with looking at the recycling infrastructure that's only in Europe with PV cycle, we're looking at sort of the first cascade, sort of recycle C1 in the diagram, where essentially the module is milled down, mechanically recycled, and then it has to be again further refined to sort of metallurgical silicon. So it goes straight back into the supply chain. But ideally, the most ideal option would be the repair or maintenance of existing PV modules. So at the moment, there's very little involvement of eco-design in first generation PV technology, considering the amount of waste that there is going to be in the future, and with more and more installation or annual installation of PV technology, there'll be a subsequent number of waste in the near future. So I've just left you with a placeholder image at the end of the presentation here to show sort of the harsh reality of some of our green energy. So we have like PV modules in landfill and some of the crushed modules. And then I've also included there some wind turbine blades as well, just to sort of showcase that we have to acknowledge the end of life stage and how we can recycle some of these technologies. I've also just included, for anybody interested that maybe doesn't get to ask a question, some of the publications in the area and some contact links as well. So thank you very much for listening.
Thank you so much, Charlie. This was amazing. Every technology has pros and cons, and I'm sure PV, and I can see that in the attendees, Professor Hari, they can go on asking many things to you as being a prolific user of PV technology, which we'll do in Q&A. But every technology has cons, and as you have rightly stated, their recycling is a pertinent issue. Likewise, we have in construction industry cement as being one of the major contributors to the carbon emissions. So we have next and the final talk for the day given by Kirthika, who will share some perspective on how can this challenge be handled and tackled. And then we will have a Q&A session.
Is my screen visible?
Yeah, you can make full screen and go ahead. Yeah.
Hello, everyone. My name is Kritika. I'm currently a postdoc researcher at LSBU, working along with Dr. Sara. So today I'm going to talk about net zero cements for sustainable constructions. As we all know, cement plays an important role in daily life. It is used in building roads, buildings, dams, bridges, etc. in almost everything that we see. However, it is important to know that it is also a source of carbon dioxide emission. And it is said that around 3.5 billion tons of cement is produced every year around the world, which actually emits around 622 kg of carbon dioxide per ton. And also, it is expected that by end of 2030, the demand of the cement production will increase up to 5 billion tons of the worldwide. And so in whole of the industrial sector, it is actually said that the cement industry contributes around 7% of the global anthropogenic CO2 emission with the amount of carbon dioxide release. And this is majorly depends upon completely on the production of the cement, the type of kiln that we use, and the fuels that we used that we are using in the kiln. So typically, if you see, over half of the cement carbon dioxide emission is from the production of the clinker, which is one of its major components. So what is the main principle is the limestone, which is used as a raw material, is calcined at a high temperature around 1400 degrees Celsius at the cement kiln. So because of this chemical reaction, the carbon dioxide is released. Further, 40% is usually released due to the burning of fuel, which is due to the requirement of the heat in the kiln for having this chemical reaction calcination to take place. And lastly, 10% is usually due to the fuel needed for mining and the transportation of these raw materials that are used for the cement production. Here in this image, if you can see, it's a typical example for a cement factory industry, which I have given at each stages how much energy is used and correspondingly how much carbon dioxide is emitted. So knowing all these things, what are the solutions? Usually, now, recently, if you say that the trends are moving towards 4 basic solutions on which the industrial trending and as well as the research and development are moving forward. Let us go one by one. First is carbon capture. Carbon capture sequestration. Inherent production of cement involves the release of carbon dioxide. So preventing is highly difficult. So what we can do is that we can construct such a plant or any type of material that can be attached to the cement kiln and could capture the carbon dioxide actually releasing from. So as far as people have researched about this carbon capture, they have said that it is a very viable technology which can reduce around 60% of carbon dioxide emission. But it is not developed or it is not deployed in many countries or many cement plants. Also, this is because it is still under the different developments. And as you can see here in the image, I have given 4 different methods or 5 different methods by which also this carbon capture is usually done, like calcium looping, oxy-fuel combustion, amine scrubbing, bio-inspired, direct capture, everything. So these are still in the laboratory stage, and few are actually in the technology in the cement industries also. The next solution that we can say is that alternative fuel. Cement production is an energy intensive requiring about 3.3 gigajoules of thermal energy per ton production. Instead of using carbon intensive fossil fuels, use of alternative fuels such as biomass, electrifications, and hydrogen based fuels will be more eco-friendly and effectively. However, if it becomes the high cost expansion for the installation, using municipal waste recyclable material is also has been considered as one of the viable, which becomes a value added product as an alternative fuel. The next solution is as we all know, as I said, that the clinker is the main culprit for CO2 emission in the cement production. So cutting down its usage by substituting it with a different type of supplementary cementitious material, such as hydraulic material, for example, like slags and coal bottom ash, is very important. Or by pozzolana, like you have fly ash, you have metakaolin, clay, such type of amium. But however, researchers have found is that the 30 to 40 percentage of the clinker is only or can be substituted instead of complete clinker production without compromising the strength of the cement. So otherwise, there is a huge problem of reduction of strength as well as the durability problems. Nowadays, in this supplementary cementitious, the name called LC3, that is limestone calcined clay cement, is one of the recent technology by which the supplementary cementitious material is been moving towards forward, and that has proved that 50% of the clinker ratio can be substituted. And last but not least, the final important solution for carbon capture is that carbon geopolymer concrete, or you can otherwise say a cement-free concrete. This is actually a final product, and it is an inorganic polymer formed through polycondensation reaction of certain waste material containing aluminosilicate, such as silica fumes, rice husk ash, or metakaolin, with alkalis like sodium bicarbonate or sodium hydroxide. So using this polycondensation reaction, the geopolymer concrete as a final product is it is arrived, and it is completely cement free, and it has a humorous various advantages over cement, and especially the high almost 50 to 80 percentage of carbon dioxide reduction is there. There are 10 to 15 percentage of carbon dioxide emission is there. That is because of use of electrical instruments or fuels, which is used for the raw material transportations and such an example. So at the end, I want to say as a key component, cement is becoming an integral part of our daily life. In fact, the second most consumed product globally. So pressure on the cement industry to decarbonize has increased rapidly, not only in the beneficial society, human, as well as the circular economically. So it is high time to think and use wisely the possible solution such that the cement which we use do not contribute no more for the climatic changes that we come across. Thank you.
Thank you so much, Kirthika. Wonderful. We had a wonderful session of talks, which has now concluded, and we have time for questions to be asked by our audience who are keeping us active. So there were 2 suggestions made by Peter for Dominic and for Jonathan, which I have shared with them. And I can see that one question raised by Professor Hawi is being typed and answered by Charlie right now. So in the meantime, if there are many questions, other questions from people, they can either type those or directly ask them by turning their audio on. So now the floor is open for Q&A, and we have, I think, about time for 2 to 3 questions. So one question, Kirthika, for you.
Yes.
About this new generation of cement, how far is it to reach to the commercial level? So that like the TRL is fairly low, between 2 to 3. When do we expect, or can we expect this to reach by 9? Or what are the biggest challenge in escaping the death valley of innovation?
So in this, out of the 4 possible solution, especially the 4th one, geopolymer concrete, it is already commercialized, and it is already in even in India or any other many places. They have made using geopolymer concrete as a road, as well as a form of a bridge. But what is that there is a huge amount of problem of setting of the cement, as well as the transportation process. So because we are using a sodium hydroxide and sodium bicarbonate as an alkali activators, which actually increases the setting time of the cement. So there is very less amount of time is there before you utilizing them together at the site. So nowadays the trend is moving towards to make of ready to mix geopolymer cement. But it is under developing stage, and it's only few research is going on in making geopolymer cement. But coming back to carbon capture technology, usually nowadays, even in UK, there is something called there are plants which are using oxy-fuel consumption, as well as they are using a biomass, it's called some bio material, because which actually helps in capturing the carbon dioxide. And in UK manufacturing, cement manufacturing, the company named Cimex, it's actually also using hydrogen as their fuel in the clinker. So these parameters are already in the stage of end user stage. But however, still the viable technologies are being practiced, has been researched.
Okay, great. Is there any final question before I invite our director, Professor Matthews, to say some concluding remarks? If not, then Alan, I would like to now share my podium with you, and then actually invite you to say some words about our presentations and about the DSM efforts to organize this event.
Okay, thank you very much. Can you hear me okay?
Yes, Alan, we can hear you.
Yeah, I'd particularly like to thank Saurav and Pamela for putting this together and worked so hard to select the speakers and make sure that this went smoothly. And Saurav in particular has put a lot of effort in, part of it from in India. So anyway, what I'd like to do is just say a few words about the Digitalized Surface Manufacturing Network Plus. That's funded by the Engineering and Physical Sciences Research Council, and its aim is to bring together academics, particularly in the UK, but also worldwide, to engage with industry and to improve the digital uptake. And we've always had one of our main aims is to involve early career researchers. And obviously we've achieved that today. And this has been such a success that we're now going to adopt this model for some future workshops and engage other early career researchers and even possibly some of you again. In terms of what digitalization can do, if you do a Google search and you put in 7 wastes or 8 wastes, you will see the benefits that digitalization can bring. It reduces waste in manufacturing and improves productivity and improves value added. And we also realize that coatings can have a profound effect on the materials and resource conservation and on sustainability. So that was part of our thinking behind running this workshop, and to celebrate the COP26 event, which is almost upon us. So, as I said, we decided to call upon early career researchers to speak, especially since the challenges are most acutely recognised by ECRs. You're the people who've got to take us forward to try to overcome the challenges of climate change. And so the workshop has perfectly illustrated your understanding of the issues and how your own research is tackling those challenges. As I said, the talks have been so impressive that we're going to invite a couple of representatives of today's speakers to a larger event in a few weeks' time, at which there will be speakers from various fields, including politics, industrial and energy policy. And then those two ECRs that speak at that larger event will be representing you all in a way, and will show those people, those tended not to be early career people, just in what good hands their future research is held. And I think we can be more confident now, having heard these talks, that we are addressing the challenges very effectively. So I think I'd just like to finish by thanking you all again, most sincerely, for all the excellent talks, and the diversity of the talks has been fantastic. And I think, as I say, Swarav and Pamela can be delighted with the fruits of all their efforts in bringing this together. So that's all I really want to say, Swarav, and thank you again.
Thank you so much, Alan. I mean, I'm grateful that you are basically giving me the credit for the success, but I think it was impossible without your proper guidances, including that of Ash and Adrian, who have been a silent backbone support to all of this success, and we continue to strive to achieve more in the time to come. So I hope everybody enjoyed this event, and as Alan has rightly said, we really enjoyed each and everyone's contribution. It was really impressive to see how these new technologies have really transformed, or are at least going to transform the future from here. And we look forward to see some success in the time to come with all the feasibility studies that we have been awarding through various projects to various institutes. So with that, I would like to conclude today's session, and would like you to stay subscribed to the DSM network through Pamela, and we look forward to bring you more depending on your feedback for this event. So thank you, one and all.